Hello, everybody. This is a brief introduction into wave functions for the introduction to quantum mechanics. Um, this is just good, solid notes with some good examples. I'm going to get right to what's important. I went into a little more detail in class. This is just what you need to do. So the first step is the wave function is psi as a function of x and t. We'll just do one dimensional right now. And the wave function, in a way, has no physical meaning on its own. It's a way to get information. From it, you can get things like energy, momentum, and probability. There's actually other things that it can give you that we may or may not discuss later, but these are the big ones. So it contains information, but it in of itself doesn't have physical meaning. It's a mathematical tool to obtain physical meaning, and it works extraordinarily well to do so. Is a cool summary of quantum mechanics. The first step is realizing that if we take the absolute value and square it, it's the probability to find the particle at a specific, that's an at, position and time. And I showed you some examples in class, and I'll show you some examples here as well. Now, the important formulas that you're going to need to know are that kinetic energy, we're moving slowly, so it's just 1/2 mv squared. Easy, momentum is mv. These classical equations still apply, which is extraordinary. On question 7b in the homework, which I'm actually going to address first, on question 7b in the homework, if you want to pause the video and take some time to find that, I ask about showing that kinetic energy is p squared over 2m. Feel free to show that once again. You can also plug in the values of h bar omega into kinetic energy and h bar k into momentum, and you should get this result. I'm doing the question for you right now because I think it would be a little confusing. That h bar cancels with that h bar squared, and you get h bar k squared over 2m is the relationship between omega and k. So this is how they are related to each other in a massive particle situation. So for massive particles, that's how they need to be related. I ask, I think the way I worded it was, do the two worlds have this in common? Yes, this is same for classical and quantum. And that's a big deal in the sense it's a boundary, or it's a bridge between the two. That's about the only bridge that exists. This relationship between kinetic energy and momentum is the same for both, and that's a pretty extraordinary result. Just keep in mind that when you do kinetic energy, and here's where it differs, and momentum, these velocities is the group velocity. And the group velocities you might remember from class is if you have a wave packet, the group itself is this like bundle where the top of a crest moves at some phase speed. Vp is phase velocity, which is completely different from the motion of the group itself. Now, those might be the same for light. For a photon, it seems that they are the same. But for an electron and most massive particles, they're actually certainly not the same. They can't be. If they were the same, then these equations wouldn't work. which I showed in class, and I'll just save that for now. You don't get the same answer for certain things. So v equals f lambda, you cannot use, that is phase velocity. It's a correct equation for phase velocity, but it's not the same velocity as in these equations. So this velocity is not these velocities, because this velocity is the peak, right? That's the phase velocity, whereas this velocity is the group, the particle itself moving, which is a combination of many different sine waves, as we saw in class. So these are group velocities and still match the classical, which I think is interesting. Please, for 7b, comment. So now, and then you are going to comment on this. What do you think about it? What does it make you think of, right? Comment, connect it, connect, right? Connect the dots, make sense of it, right? So your job for 7b is to make sense of this in whatever way you can. You know, this is a new way of looking at the universe, yet there's a bridge to something more familiar. You know, take a moment, you know, beyond the equations and just connect it for a second. That was the reason I wrote the question, was to like ground it for a second. Anyway, back to the equations you're going to need. So I think you're going to need a few things going forward. Of course, you're going to need to also know that kinetic energy is h bar omega, where omega is 2 pi times the frequency. H bar is the reduced Planck's constant. That's h over 2 pi, which I've written on your homework, is 1.05457. I'll get exact, times 10 to the negative 34 joules per second, joules times second. Squeeze that in there. That's your h bar. The reason is we're dealing with sine waves, so that 2 pi, because of the radians, occurs everywhere. So this is really common to do, and I'm going to adopt it. I think it makes it look neater. It's the most important constant in quantum mechanics. So let's do it. Let's do quantum fully. So Ke is h bar omega. Momentum is h bar times the wave number. We've shown that in class the first day. If you remember, we did that the first day, where the wave number is 2 pi over the wavelength. There's your equations. And if you want, you can add this one, Ke equals p squared over 2m, but that just comes from this. And there's your equations, guys. There you go. That's what you need to know. Pause it, write it down. Hope it makes sense. Now I'm going to show you one or two things just to conceptualize it. And then I'll do another video with an example. So the wave packet idea is that if you sum, this is a sum of 1 to 5, I'm changing n2. If you sum a bunch of sine waves, which is kx with a little divisor there, minus omega t, and the omega has a little divisor, and I changed that on purpose for reasons that make sense. And I'm hoping to find an article that summarizes it well, but just for now, if you sum a bunch of sine waves, you might notice what happens is that it becomes more localized if I increase the number of sine waves. And if I go from 50 to 500, I'm almost like I've saturated it. And if I keep adding more, it doesn't really change it much. So I might as well just go back to 50. It gets the point across, right? And so the idea is that this can move, right? You can see it moving to the right. It still moves because it's still kx minus omega t, but here's the point. And here's what you should write down, right? For a single sine wave, right? For a single sine wave, sine kx minus omega t, a single one, careful, single one. A single sine wave since the value of k is known, the momentum is h bar k that is known. In other words, the uncertainty, and this, by the way, is standard deviation for anybody who knows statistics, the uncertainty is 0. So if I have sine x is omega t is the wave function, then I know its momentum. But I don't know its position, right? Its position is anywhere. So delta x is infinite. Now, if I do psi of xt, I'm just getting rid of the t so I can write here, is the sum of many sine waves, like I did right here, then I get it more localized, right? I get it, right, more localized, right? Where the probability is more localized at a specific point. But if I added many sine waves of different k values, then the momentum is more unknown. Delta p is larger. Delta p being the uncertainty, right? The breadth of the values of k that I used. Right? So you can think about it as if I graph p as a function of, if I graph k, or if I plotted all the values of k, right? There's a lot of them. So I'll just put it like this. Delta p is larger. It's more unknown. But delta x is smaller. So delta x and delta p go inverse of one another. To localize a wave packet, you need to add different values of k together in sine waves. And what that does is it makes delta p, or momentum, more unknown and x more known. So localized means I know x better, but I know momentum worse. So we can't ever know a particle's momentum and position at the same time. That's called the uncertainty principle. And this is pretty much the proof of it. You have to do a more general formula for how you do this, and you do a standard deviation, and you can show that as you localize a wave packet, you have to use different values of k. And if I actually had, you guys ready for it? I'm going to go back to here. If I had, right? So if I know momentum, meaning an exact value of k, which means an exact wavelength, if that helps, right? Wavelength is momentum, I think is maybe a tricky concept, but the formula here is P equals H over lambda, which is the same as H bar K, because K is 2 pi over lambda. Take a second and remind yourself of that. That's where this comes from. If I know P, what does that look like? That means that's a sine wave, right? That's my psi of xt. X is unknown. And if I know x, right, I have infinitely many k combined, which means that my value for psi of x of t is like this peak. It's called a delta function, for those who are into math, right? A pure delta function. And it's called a Fourier transform, which is kind of fun. You do a Fourier transform to turn anything into its sine waves, meaning if you sum up sine waves, you can get any shape you want. A mathematician named Fourier figured that out. And if you do a combination of sine waves, you can get a peak. I just kind of showed you guys that on Desmos. Right? And there's a way to do it where you just get a straight up peak, where I know that this x naught or whatever position I want, I can put my particle there. But it's infinite. I need infinitely many momentum to do it, which means momentum is completely unknown. Because there's infinitely many k, I don't know the momentum. So to localize a particle, you don't know its momentum. And to know its momentum, it has to spread out everywhere in the universe in probability. That's called the uncertainty principle, the Heisenberg uncertainty principle. I'll just write uncertainty principle just for brevity. Uncertainty principle says that what you don't know about x, or the standard deviation, technically mathematically, times what you don't know about p has to be greater than or equal to h bar over 2. Now, there's proofs that require some a little more mathematical rigorousness to it, but I hope the concept was clear. If you understand that k is wavelength is momentum, and that to get a localized wave function, say to get a localized particle where all the probability is there, so you know it's there, you can't know its momentum. That means it's infinitely many sine waves combined. So you can't actually know both at the same time. This is called the uncertainty principle. Pause, rewind it. I hope that makes sense. That's kind of a cool thing. I was hoping to get to it in class. I will at some point. We're going to use it. It's a big deal. It's one of the fundamental principles of what results in quantum mechanics. Stay tuned to the next video. I will do some examples of energy and momentum. I love you very much.